Welcome, students. So we have discussed a lot of things about quantum mechanics in the last session. So this is the detailed course on quantum mechanics. So today we will have lesson number 4. So in this lesson we will discuss mainly two important topics. So once we start, in the last lesson we have discussed about the Hermicity of Hermitian and a few other things. So I will start straightforward now. From the conservation of probability, we have discussed a lot of things, and from that, we have to conclude an important topic today. So, first, write the heading conservation of probability. So, as we discussed in the last sessions, that the normalization condition for any probability system, we have probability of PR, T, R is the space part, T is the time part, D tau. The integration in the entire space it should be 1. And we have also discussed that probability is in terms of wave function can be written as psi rt model square. So this is very simple that psi star rt and psi rt gives you the probability. So now if we integrate this system with respect to t, what will happen? So this is our probability density. Probability density. Okay, so now if I integrate, so here we have psi star rt and psi rt in this other side. So if I integrate this thing, we have to take first and second function. So in this case, we will get is psi star rt. If I choose as a function 1, then I have to differentiate it second function with respect to t, and then we will keep psi rt as a constant, differentiate it with respect to t psi rt d tau. So this is what we are going to get. Okay, now with these equation, we also know the Schrodinger's equation in 3 dimension. These are all 3 dimensional system because we are taking R. So in 3 dimension, we know the time dependent Schrodinger equation also. So we will write that first. For 3 dimension system, Schrodinger equation, which we have discussed in our previous sessions. This is simply a postulate. It is equal to iota h squared del psi rt over dt. This is the Schrodinger's equation. And now if I want to take its complex conjugate, what will be the complex conjugate of this function? Simply del square psi rt will become psi star rt plus Vr will remain as it is. Psi rt will become psi star rt. And iota will become minus iota del psi star rt over dt. So these are the two equations we are having. Schrodinger's time dependent equation in 3 dimension and its complex conjugate. Now you see, from this equation, we can say this equation number 1, this is equation number 2, and equation number 3. So if we compile all these three equations now together, if we put the values of d psi over dt here, d psi star over dt here from these equation number 2 and 3, so what we will get this function as, so integration of probability function rt dt will become, see, here we have this psi star rt as it is, then del psi rt over dt. So this is what we are going to put in this equation. So if I do that, first function I will get is minus h cut square upon 2m. So, and here this vr psi rt, and here we have vr psi star rt. So let's quickly put out. So first of all, you see h cut square over 2m is the one thing which is common. If I send this iota h cut in the other side, what we are going to get? Minus h cut upon 2 iota m. So this I am taking outside. Then in the inner part we have having psi star rt, and then this in place of this d psi rt over dt we have is del square psi rt. This function we will deal later. So psi star rt del square psi rt. Then in the other part, here we have is del psi star over dt, and here also we have del psi star over dt. So we will replace this value from this equation. So if I send this iota h cut in the other side in the division, so what we will get here is plus h cut over 2 iota. So but here we have taken minus h cut over 2 iota common. So I will take this sign as a minus, and now inside we have is psi star rt and then psi rt. Sorry, del psi star over dt, this we have is del square psi star rt. So we have minus del square psi star rt, and then we have is psi rt separately, and then we have is d top. With the integration sign. And the entire volume we can say. And what will happen to other function? Vr psi rt. So here if you see, if I send this iota h cut in the division, and here it is negative iota h cut, so these two will cancel out each other if you put it here in this space. So that is why we are not writing the other term. This term and this term will cancel out due to the negative sign, and this will multiply with psi star, this will multiply with psi. So obviously function will also become same. So this is cancelling. Okay, so now we get this equation. So now we can rearrange this equation with the h cut over 2 iota m common, and we have integration. If I take one del function common, so this equation will change. We have a psi, so del psi star deta. This is what we are getting. Okay, this whole quantity inside the bracket, this we will replace with J, and this is basically called probability current density. So here we have probability function dt theta that is equal to minus integration of v. This whole quantity we will replace with j, including this h squared over 2 iota m. Here, sorry, we have minus sign also. So what we are getting from this is del dot j dt. So here j is basically probability current density. So we can write j, we have a psi star, including this h squared over 2 iota m, psi star del psi minus psi del psi star. Okay, this RT value remain. You can write the RT value. Otherwise, for simplification, you can directly write psi star del psi minus psi del psi star, just to remember. This is the very important formula you always should remember. Probability current density, how to calculate. A lot of time you will get a question in GATE examination and in CSIR both from this topic. Okay, now from this if we see, if we remove the integration sign and rewrite this equation, what we are going to get? Let's discuss that. Please write everyone quickly. If anybody having any doubt, please write in the comment box so that we can discuss in the next session. Okay, and also please share this video with your friends, because this all quantum mechanics course is free of cost. So this will be very useful for the student preparing for CSIR NET and GATE examination. So now we have integration d over dt. Here we have PRT first. And then if I take this negative del j in the other side, so it will become plus del j d tau, and the other side becomes 0. So from this we can say dPRT over dt plus del j is 0. This will be a non-stationary state. Non-stationary state. And also this equation is called as continuity equation. Everyone knows, very important equation, continuity equation. So what is the condition for a stationary state from this? This state will become stationary if any of this thing becomes 0 out of these two. So del dot j should be 0. Okay, this will be the condition for a stationary state. Or the stationary state. So this is very important form. We can change this equation in another formats also. This del PRT over dt also if 0, then also we can say the stationary state. We can say for stationary state that del PRT over dt, this also could be 0. So this is very important. Now we can change it into another forms. Del dot j I can write as so now we can convert it into the closed loop j dot ds with the appropriate theorems, and here we have closed integration j dot ds is equal to 0. So what this represents? If psi, the wave function, is real, then probability function, the probability current density basically, probability current density will be 0. That is, J will be 0. How? We will take the examples. So these are the very important conclusion from this topic. And now we will take some question and then proceed to the next thing. So do write this and then we will proceed. So as we know that probability current density Z we have is h cut over 2 iota m psi star del psi minus psi del psi star, that is equal to 0 for real wave function. So how it is? For an example, if you take psi is equal to a exponential of kx, suppose. So what will be its psi star? Its psi star will be also same because this is a real function. So you can change the constant as a complex constant, but exponential part remains same. So if you find del psi or del psi star, both are same. Okay, del psi will be equal to del psi star. So then we don't have to calculate anything. We can just see psi star is also similar as psi. Just constant is there, but a and a star will be also a square. So this will become again real. So everything will cancel out each other. So in that case, J is always 0. But for any other function which is not real, suppose like we have iota in place of only kx, iota kx, so then what will happen is psi star will be now different, exponential of minus iota kx. And that small difference is enough to make J non-zero. So as we have now, for J to calculate, we have to calculate this del psi and del psi star. So first suppose if I calculate del psi, then we simply have is d psi over dx, that will become exponential of iota kx dot iota k, and we will have del psi star as del psi star over dx, and that will make it negative of iota k, and then again similar a exponential of iota kx. But this negative sign, if you put here, it will become positive and this will give you a non-zero value. So I am writing in the next slide that J will become h cut over 2 iota m multiplied with. So first of all what we have is psi star as it is, so psi star and del psi. So this a and a star will become a square first. Then we have is exponential of iota kx with negative sign, and here we have del psi also with plus sign. So this exponential will cancel out each other, and only thing we will have is iota k. Iota k in the multiplication. I am writing it directly. I hope this is very easy step, everyone will understand. And now we have to write is, you don't have to compare with equal to 0. Okay? Only this equation you see. This is 0 for wave function which is real. Okay. So then we have on the other side is minus psi and del psi star. So from this minus and this minus we will get a positive sign, and here what we will have is again a and a star will make it, now this time you have to take del psi star and psi. So a square you are getting for sure, and here you are getting is iota k, again exponential of iota kx, and here sorry, there is a negative sign that I missed. So So this negative iota kx and this iota kx will cancel out each other. So we get here is only iota k. So that means we are getting the probability current density as h cut over 2 iota m a square iota k and iota k added as 2 iota k. So we are cancelling few things. So j become h cut k a square divided by m only, 2 iota cancels. Okay, so this is what we are getting for this function. So this is very important, that how to calculate the probability current density. I hope you got these things with this basic example. So for this you should be very much perfect in the differentiation which is required here. So any function if it is given, if you know that function differentiation, easily you can calculate the probability current density. So you should work on your differentiation part also a little bit to solve quantum mechanics problem. So that is why quantum mechanics has a very good relation with mathematical physics. So both subjects you should read carefully. Okay. So if we talk about the units of probability current density in one dimension, in 1D if we talk, the probability current density will become L minus 1, LT minus 1. So the unit for probability current density in one dimension become T minus. Okay. If we talk for only one dimension, from this we will be calculating. Okay. Now for 2D, these all things you can also directly remember. For 2D I am writing it directly. It will be L minus 1, T minus 1, and for 3 dimension the unit we will have is L minus 2, T minus. Because we have talked about the wave function dimensions in the last sessions. From there I am writing directly. Okay, these are basically the dimensions for the probability current density. Okay, so few questions I am giving you as a homework. If your psi x, you have to find is probability current density. I will be not discussing these questions. This is your homework. You have to find the probability current density for this. Second is and third lambda sin kx. So all these three questions are your homework. Okay. So this is what we are finished with now. The probability current density concept from the conservation of probability. Very important topic. Now we will move to a very important concept. This is a very important concept to understand the basics of wave function and bounded and unbounded system. So now we will talk about this bounded and unbounded system. Bounded and unbounded system. Very important topic. You should see this part very carefully so that you can understand a lot of things. Bounded and unbounded system. Okay, so to understand this, what will happen in bounded part and what system you will say unbounded, and then what will be the nature of the wave function in bounded and unbounded systems. These are all things we have to discuss very carefully and in detail. So we will first take a general potential so that if a potential is negative, positive, or zero, we can understand all the dimension of potential. Okay, how the potential change, and if with energy and potential, we basically decide the bounded or unbounded condition. So I'm taking a general potential system. Suppose it is like this. Okay, I can change the color. Wait a second. Okay, if I take the potential shape, suppose like this. We can make even little. Okay, that's okay. Suppose like this, we have the potential Vx generalized potential. I'm taking. So in this case, I have taken a negative potential, a zero potential, and a positive potential. And now I will take different energy levels. Okay, because particle energy could be different and system energy could be different. So if this is our potential system and energy of the particle is different, then where the particle is bound, where the particle is unbound, these are all possibilities we have to look for. So in that case, you know, suppose I take first energy level here. E1 energy level. So E1 is particularly here, you see this remains less than the potential V in all the cases. Okay, value we have not decided anything. Okay, it could be anything. So just numerically you can write, but not necessary. Suppose I take another energy level, and I can keep the same. So this is the another energy level here. See, in this case, here energy is less than the potential. This is suppose over E2 we have. Okay. Here the energy is less than the potential. You see the potential is above the energy level. But here E is equal to V, E2 is equal to V potential value. And here the energy become greater than the potential. You see. Then how it will change the concept, we will discuss how it will help us to figure out the bounded system or unbounded system. We will discuss in all detail. But first we will choose different energy levels. So you should understand that energy here is greater than potential. And again here, after this point, the energy become less to the potential again. Okay, and I take another energy level, suppose which is somewhere here. So with these three different energies, we can generalize our concept in very much detail. So for the energy, E1, E2 and E3. So here you see E3 is greater till this point to the potential, but after this point, E3 become less to the potential. So what will change and how the things will change, we have to understand very carefully. Okay, so this figure you quickly make. Now, if we talk about the energy level E1, see, for energy E1, how the motion will be decided, we have to talk about this. If you remember, we have discussed earlier a topic, a very important topic that when the wave function will be oscillatory and when the function will be a linearly decaying kind of nature. Classical turning points, if you remember, guys. See the first lecture if you don't remember, first or second. So there we have discussed that if the kinetic energy is negative or positive, that will decide the nature of the wave function. So you should see that particular lecture if you want to understand this topic in detail, because I cannot tell you all those things again. But yeah, if the kinetic energy is negative, we have discussed that the motion is non-accelerated. So for the energy E1, you see E1 is less than V. So kinetic energy here is negative. So the motion is non-oscillatory. Okay. So in that case, how the motion will be, that we have to check. So here we have d2 psi over dx square, the one dimension sound is the equation, simple, 2x per square v minus e psi, if you remember. So here if v is greater than e, here you can clearly see the v is greater than e1, so in that case this side will be positive, and if this side is positive we get the differential equation as d2 psi over dx square, some positive constant with psi. So here we have is d2 psi over dx square, some positive constant, suppose alpha square, and here we have is psi. Okay. So this is a simple differential equation. As I told you that mathematical physics is very crucial for the quantum solutions. So here this is a simple differential equation. Here you have auxiliary solution. Alpha square here, so m1 will be alpha and m2 will be minus alpha. And if you take the auxiliary solution for this equation, psi 1 x will become a exponential of alpha x, and psi 2 x will become a exponential of minus alpha x. So how we will use this function in the given potential system, potential and energy system. So here you see clearly this, a very important discussion is going to take place. See the things very carefully. I will choose 2-3 points on this potential. Okay, very important. So if I take a point, suppose here, here and here, just for example, okay, this will not make much difference because in all the cases potential is greater than the energy value. So this will not make much sense. But if I take a particular region, suppose this point and suppose this point where it is equal energy and potential. Okay, so this I will take as x1 and this I will take as a x2 point. Okay, corresponding to this we have to discuss a lot of things. So I'm taking these points for E1 also. Okay, for E1 also I have these 2 points x1 and x2. Okay. For x1 and x2, if I want to decide how the function is changing, I have two different wave functions here, either this or this. Psi 1x is exponential of alpha x. So if I draw this part, you see this will be going like this at x1 and x2. So which part could be allowed here? This side cannot be allowed because this is going to infinity. So the wave function which could be allowed for our purpose in this exponential of alpha kx is this one. From minus infinity you can take to infinity. Similarly, if you take the other function at x1 and x2, how that is going to vary? Simply the opposite of previous one. This time you need to cancel this part. Why need to cancel? We have discussed a lot of things that wave function should not diverge. It should vanish or become zero when it goes to infinity. So here this side is going to infinity, the wave function itself, but this could not be a possibility for a valid wave function. So this side we cannot take for this part, and this side we will not consider for the other case. Okay. So here we can conclude that psi 1x and psi 2x, both you see, this is diverging here, this is also diverging in the other side. So psi 1 and psi 2 both are violating for a wave function which should obey. So psi 1 and psi 2 violates. Okay. The condition of wave function to be finite array. This is what it should follow. Okay. So here these solutions which we are getting is not favorable for us. So these solutions are not possible. So for even energy, no quantum mechanical solution exists. Very clear. It should be very clear, guys. In this case, for the energy E1, there is no possible solution because everywhere kinetic energy is just negative. Okay. But now the most interesting part, which is E2 energy. Okay, if you understand E2, we will write directly for E3. Okay. For E2 now we will discuss, and this is a very important concept. This will decide your bounded system and unbounded system, very clearly. So now moving forward, for E2, for E2 energy, you see, we have two turning points. For E2 energy, we have two turning points. One is x1, another is x2. What is happening at x1 and x2 is energy become equal to the potential energy. So basically kinetic energy is 0, and the nature of the kinetic energy is also changing. Here you see E is less than V. Here E2 is greater than V, and again E2 is less than V. So when you come from this region to this region, the nature of the wave function will change for sure, because kinetic energy sign also changing. So in this case, at x1 and x2, we have E is equal to V, energy equal to potential. So then you know this could be written as the lambda value, which is h over p. Okay, de Broglie wave function. So from that we can write h is equal to p, we can write as root 2m e minus v, very well known function. Here you see e is equal to v, so this will become 0. So this lambda will be kind of singular value. Okay, so here singular results you are getting. So de Broglie wave function is single. Singular means like blowing up, going to infinity, or very large value, you can say. Right? These are the classical points we have discussed. What these are having meaning and all this we have just discussed in our first or second lesson where we discussed the classical turning points. So if you have not seen the first two lectures, please go through that. Okay. Now we can define the classical turning point again. If somebody just missed the previous lecture, classical turning points is a boundary where classical allowed region change into classical forbidden region, or it could be opposite or vice versa. Okay, so this is a very important factor and definition you should remember. So now what we are having is, in this case, if we study this x1 and x2 values, very important guys, should understand very carefully. This time we basically don't have to discuss any mathematical calculation. Directly we can understand a lot of things. Okay. So this is what we have. Here you see the nature of wave function will be like this. Okay. Because before x1 e2 is less than v, and after x2 e2 is less than v again. So we understand from our previous discussion, when the kinetic energy is negative, wave function is exponentially decaying nature. If you remember guys from the previous lectures. Otherwise I have defined here also the classical turning point, but you should watch the recordings as well. Okay. And after x2 the nature of the wave function will be again classically decaying. This also very well you should be clear. But in between, what is the nature of the wave function? Here, how we will decide that? You see, the E2 is greater than V. Here kinetic energy is positive. Here kinetic energy is negative. Here also kinetic energy is negative. So in that case, if positive kinetic energy we will have the nature of the wave function is oscillatory. This we have discussed in very much detail. Okay, so we can make it a little good. Wave function nature is oscillatory. So how it is oscillatory, we have discussed in quite good detail. Wave function nature is oscillatory. And this is called the bounded region. You see, in the bounded region, you are getting a oscillatory solution. Oscillatory solutions means you have different bounded states. Okay. So, very important conclusion. Okay, so for different energy values, you could have for a particle, but those all values will be in continuum form and quantized. Okay, and the energy will be discrete. Okay, you can write also quantized and discrete values. Discrete energy levels or values. Okay, so this part is your non-oscillatory. You could say. This part is again non-oscillatory. Okay, and obviously classical forbidden also, as we discussed. This is also classical forbidden. But the mid part from x1 to x2, this is oscillatory in nature and classically allowed. Classically allowed region. So this is for E2 energy. For E2 energy, this is only there. Okay. So now what we will have is next thing is E3. You see E3. So for E3, can you directly make it? For E3, we have here E3 is greater than V. So that means kinetic energy is positive in this region. And here again kinetic energy become negative because potential become greater than E3 energy. So in that case, what we can have is a direct wave function nature. How? For E3 energy, only x3 point you can take here, okay, which is suppose somewhere here, where energy is equal to potential. So this will be the another point x3, which is a turning point. So before that, the wave function will be of what nature? Oscillatory, positive kinetic energy, here negative kinetic energy, it will decay. So the wave function nature for this particular energy E3, you will have the oscillatory nature before x3, and after x3 point, you have simply exponential decay. Okay. So this is what you have the wave function psi x nature. Sorry for the this is psi x. For E3, E2, and E1 energy. So I hope you are very much clear. So this is your bounded system. Okay, this region is your bounded because you see exponentially nature here, exponentially nature here, and in between you have an oscillatory nature. So this portion basically, this system is not bounded. Okay, this system is not bounded because this side you are having only oscillatory nature, and this side you are having a exponentially decaying. There is no bounded part you are seeing like this. So you see from the potential also you can clearly see this is where the function should be kind of bounded region. So this is kind of a very important discussion we had. So I hope you understand this particular discussion. So if you have any kind of potential system, then you can draw its corresponding wave function very easily. So for an example, if I take a potential system which is like this, suppose Wait a second. I will take simple example like suppose okay, this kind of potential. So this is your suppose zero value on the scale A. Here you have 2A. This is your potential value. Okay. So if the potential curve is like this, how will be the wave function going to vary? That you have to decide. So basically, you need an energy level to decide the wave function for sure. So I will give you energy level. If you change the energy level, wave function nature will accordingly change. So we will take the most significant possible kind of energy. Suppose energy is here, energy level is here. So what kind of nature of this wave function will be? So you can draw the wave function on it itself. How? I'm drawing the wave function on this. See, here you see potential is here. Okay, this is your potential value. This red curve is basically defining the potential, and in this region, from minus infinity to 0, E is less than V. So kinetic energy is negative. So wave function will be kind of oscillatory nature till this point. Exponentially decaying nature. But when you reach to this point, here you see at this point there is a sudden change and potential goes to negative. So here kinetic energy become positive. Here your kinetic energy is negative, exponentially decaying. But here the wave function will be kind of oscillatory nature. So you can simply make oscillatory behavior of the wave function. Okay, till this point. But when you reach this point again, there is a sudden change in the potential that reach to again higher value positive. So here kinetic energy become again negative. So wave function become again decaying nature. So you go till 2A and stop and see again. Still potential is above the energy level. It will keep continuing decaying like this. Okay. So this is what you are going to get in this case. This will be your wave function. Psi. For more clarity, I will take another example, and with that, we will end our session. So, if any doubt, guys, please ask in your comment box and share with your friends so that they can see this quantum mechanical course for free and take the benefits of these classes. So, for example, if I take another potential, a very simple potential, kind of this. Okay. So, how this could be? This is simply V equal to 0 and this is simply negative of Vg. Okay, now we will take the energy level. Suppose somewhere here and corresponding wave function you need to draw. This kind of question are asked in many examination, specifically in GATE, drawing wave function and all are very important. For just examination also sometime in BARC examination and at CSIR NET also. So here you see again kinetic energy is negative in this region, potential is above energy value. So wave function will be kind of exponential in nature till this point 0 value from minus infinity to 0. Then when you go from 0 to A, the kinetic energy is positive. So wave function will be kind of oscillatory nature. When you reach to this point, you can separately draw also, no problem. When you reach to this point, you have again a turning point. So after this point, you would have the nature of the wave function as exponentially decaying because again kinetic energy become negative, so decaying nature. But when you go from this side also, kinetic energy is positive. So this side and this side, you can't have like 0 and then again going up, but simply this is oscillatory nature, so exponentially decay and then little exponential growth you will have, and then again oscillatory nature of the wave function. And then after this point 3A, you have just kinetic energy negative. So this will keep decaying like this. So these are the two bounded regions you are getting in this particular potential system. So you can clearly see this is a kind of potential box. Here also a potential box which gives you a bounded nature, and otherwise it is an exponential graph. So this wave function you are getting here in this case. So there could be four options that which is the correct option for a particular wave function in this given potential system. So I hope you are very much clear. This is a very crucial topic. If then any doubt, please ask. Okay, so with that, I'm going to end this our lesson number 4, and we will have the next session very soon. Okay, so revise all these previous 3 sessions. In this session, comment down your thoughts that how this lectures going on. Is it beneficial for you or not? And if it is beneficial, please share with your other students, friends also, so that they can get benefit of this lecture series. Thank you. Take care.